Cambridge International AS and A-Level Physics Coursebook by David Hang et al. Chapter 29, Quantum Physics, Exam Style Questions. Number 1. The spectrum of sunlight has dark lines. These dark lines are due to the absorption of certain wavelengths by the cooler gases in the atmosphere of the sun. One particular dark spectral line has a wavelength of 590 nanometers. Here it is given. Calculate the energy of a photon. So your A, you have a given of lambda. Lambda is 590 nano. So that is times 10 to minus 9 meters. Right? Now we need to calculate first frequency. The frequency is the velocity of light, which is constant, divided by the lambda. Using that formula, we can have 5.08 times 10 raised to 14 hertz. This is our answer for the frequency. Now let's go to energy. Energy is equals to HF. H is a constant, Planck's constant. So we have no problem using the formula. Your F is calculated. The answer is 3.4 times 10 to minus 19 joule. So this is now the energy of the photon. Letter B. The diagram below shows some of the energy levels of an isolated atom of helium. Okay. So let me put this up. So up to this part. Yes. Explain the significance of the energy levels having negative values. Okay. I'll write the answer here. So what is the significance? Okay, this one. Electrons, it's difficult to write, have zero potential energy at infinity. Yeah. So energy must be less than zero. You can see that. Energy must be less than 0 near the nucleus. There you go. Next one, explain with reference to the energy level diagram above how a dark line in the spectrum may be due to the presence of the helium in the atmosphere of the sun. So this energy, okay, maybe to the helium of the sun. Now, first, before I explain the answer, before I write the answer, so let us find first this 3.4 here. So you can have 7.6 minus 5.8, 7.6 minus 3, 7.6 minus 2.4, and then 5.8 minus 3. You can do all the subtractions in this number. Then find this 3.4. So we know that since it is absorption, so it means to say we are moving up. Okay, so the electron gets excited to move to the upper energy level. So here it's this one is actually this one, right? This is 5.8 minus 2.4 equals 3.4. So our answer will be here. I'll write it here. Electron gets excited from 5.8 energy level, 5.8 level to 2.4 level. All right. Electron absorbs all energy of the photon. There you go. Which is 3.4 times 10 to negative 19 joule, the one we calculated in letter A. Let's go to number 3. All the light absorbed by the atoms in the sun's atmosphere is re-emitted. Suggest why a dark spectral line of wavelength 500 nanometers is still observable from the Earth. So let's move that one a little bit. So triple I, the answer is that light is emitted in all directions. That's the very reason. Light is emitted in all directions. Let's go to number 2. Okay, for number 2, the diagram below shows the energy level of an isolated hydrogen atom. The lowest energy of an atom is known as the ground state. Each level is assigned an integer number n, known as principal quantum number. The ground state has n equals 1. Explain what happens to an electron in the ground state when it absorbs energy equal to this one. So that is the lowest lowest level ground state. So answer to that is that, let me write my answer here for letter A. Okay, electron is totally removed from the nucleus. So electron is totally removed from nucleus. That is what's happened because it's the maximum energy here. Next, explain why a photon is emitted when an electron makes a transition energy of N3 to N2. So it means to say B N3 to N2. It means to say it emits here. This is part here. It's 2 points. Now, okay, the reason for that is here BI. Let me just write it here. Okay, BI. Okay, reason for that is the potential energy of the electron. Okay, of the electron. The potential energy of the electron is less in N2 than N3. So energy is given out as a photon. So energy is given out as a photon. That's it. Next, calculate the wavelength of electromagnetic radiation emitted when an electron makes a jump between energy level N3 and N2. So let's move that. Let's go to BII. BII is simply negative 5.4, okay, times 10 to the negative 19 minus the negative of 2.4, okay, times 10 to the negative 19, okay. Doing that will give you 3 times 10 to the minus 19 joule, okay. Now this is your energy, okay. That is your change in energy. Now you have a formula, lambda. Energy is equals to HF, which is actually equal to HC all over lambda. Then from this equation, we have lambda equals to HC all over E. Now we have calculated the E. Okay? H is a constant and C is a constant also, the speed of light. So here, using this formula, the lambda will give us 6.63 times 10 to minus 7 meters. This is your lambda. So that is the wavelength. Next is number 3. Okay. Use the energy level diagram to show the energy of an energy level is inversely proportional to n squared. So let's have it's here number 3. Let's put this here. So energy is inversely proportional to 1 over n squared. So it means therefore, these 3 dots is therefore E n squared is a constant, right? So let's test that one. So if n is equal to 1, then E n squared equals, it's 21.8 from the graph times 1 square. It gives us 21.8. Now if n is equal to 2, then your E n squared equals 5.4 times 4. That gives us 21.6. Okay? If n is equal to 3, then E n squared, the value of E at n level 3 is 2.4, and then 3 times 3 is 9, so that is 21.6. So we have shown that it is inversely proportional. So it is all constant here. They are very close to each other, so we can consider them, those numbers, as constant. Let's go to number 3. Number 3, here we go for number 3. Okay? And number 3, explain what is meant by wave-particle duality. So let me explain it here at the side. Okay? So this is 3AI. I think it's not writing here, so let's put it here. 3AI. Okay? Listen to my explanation here. I just dictate the answer here. Okay? Electromagnetic radiation displays both properties of a particle and a wave. That's the answer. Then II, explain how the photoelectric effect gives evidence for this phenomenon. Okay, I'll give 2 answers also. So please listen to this answer. Radiation below certain frequency will not produce photoelectrons. Energy of a packet depends on frequency, which is the property of a wave. There you go. That's the answer for AII. Let's go to B. Let's go to B here. Okay, this is B. Okay, let's make it big. Okay, here. Explain why there are no photoelectrons emitted with the frequency of the incident of light is less than this number. So let's go to B. So I'll explain. Please listen carefully. Here, this is actually here is around 5.6. Okay, times 10 to the 14th. Yeah, 14th power. All right. So here, actually going here, there is no emission here. All right. Okay. So explain. How many 2 marks? Okay. First explanation. Energy of the photon is less than the work function, which is the minimum energy required to remove an electron from the metal surface. There you go. I explained already in B. Calculate the work function for sodium. Okay. So now we know that the work function formula, work function is equals to HFO. So the FO is 5.6 here. This is our work function here. So the work function is H is constant. We know that one. Times the FO is 5.6. 5.6 times 10 to the 14. Alright? So our work function is around 3.7 times 10 to the negative 19J. So remember that your H is a constant, 6.63 times 10 to minus 34. That's it. Then we can have the work function here. Let's go to D. Okay, D. Use the graph to calculate the value of the Planck's constant. Planck's constant is H. So the value is the gradient itself. Okay, this is D. The gradient. The gradient is the change in Y all over the change in X. So what are our changes in Y? By looking at the graph here, this is your Y and this one. This is around 1.82 actually, to be honest with you, electron volt. Okay, so the change in Y will be 1.82, okay, times the E, because it's electron volt, divided by minus 0, starting from 0 down, okay. The X here is 10, okay, 10 minus 5.6. Okay, but this is times 10 to the 14th power. So now the gradient is actually 6.62 times 10 to the negative 34 joule times second. So you see, it's very close with our constant 6.63. Okay, let us go to the last number. Let's go to number 4. Number 4 is our last question here in the exam style. Okay, letter A. So this is our setup here, the cathode. You have your voltage here. Okay, calculate the kinetic energy in joules of the electrons incident on the graphic film. Okay, But first, let's have A. Explain what is meant by the Broglie wavelength of an electron. So, please listen to my explanation here, 2 marks. Okay? Electrons show a wave-particle duality. The Broglie or de Broglie wavelength is the wavelength of an electron. That's letter A. Let's go to BI. Now we do calculations here. Calculate the kinetic energy. Okay. Now the BI is here. Work is actually Q times the V. Kinetic energy is actually the work. So your kinetic energy is equals to Q times the V. Now, we know that the kinetic energy, the charge of electron is E, 1.6 times into the negative 19. You just write it in your calculator. Times the voltage, 5,000. Okay. Now, our kinetic energy is 8 times 10 to minus 16 J. That is your kinetic energy. Right. Now, let's go to 2. Show that the momentum of electron is given by this equation here. Hence, calculate the momentum of the electron. Okay. So, let me show that. Okay. Let us show that it is the formula. Okay. Kinetic energy is equals to mv squared over 2. Crisscross, that will become 2. Kinetic energy is equals to mv squared. Now, if you multiply both sides by m, okay, it's my multiply both sides by m, we can have 2 times kinetic energy times the mass is equals to m squared v squared. So mv is p, momentum p is mv. Alright, so it means to say this is p squared, this is 2 kinetic energy times the mass. So it means to say that your formula of p is now the square root of what? Twice the kinetic energy times the mass. Then we have already shown that one. Hence, calculate the momentum. Then we can calculate the momentum using the formula. Using this formula, you have your kinetic energy is already calculated at the top here. At the top, the kinetic energy. The mass of, what is this one? Mass of electron. Is this an electron? Right? Because it's electron, we know the mass of electron. The mass of electron, I'll just write it here. The mass of electron is 9.11 times 10 to minus 31 kilogram. Okay, so the energy at the top, mass of electron is given, the times to your momentum is 3.8 times 10 to minus 23 kilogram times meter second negative 1. That is your momentum. Now, let's go to letter C. Okay. Calculate the de Broglie wavelength of the electrons. So let's have the de Broglie wavelength of the electrons. So what is the formula of de Broglie? Lambda is h over momentum. Okay, or h over p. We have the momentum calculated. Then the de Broglie now, the wavelength now is 1.7 times 10 to minus 11 meters. There. Let's go to the last question. Here, C. Discuss how the wavelength of neutrons and electrons moving with the same energy would compare. Okay, same energy. It means to say they have same velocity. That is the meaning of that. Now, using our argument here, our formula for de Broglie, H all over m times the V. So now, neutrons and electrons. Okay, our topic of interest here is about neutrons, okay, and electrons. Okay. Now let's compare first the mass. The mass of neutron is greater than the mass of an electron. Right? So because the mass of neutron is greater than electron, okay, and the mass is inversely proportional to the wavelength, it means to say that the wavelength of the neutron is less than the wavelength of the electron. Okay, so you're going to say here neutron will have shorter wavelength. So neutron will have shorter wavelength. By the way, I explain it this way, but you need to write in words during examination. Thank you. Please don't forget to subscribe to our channel.